In today's video, we are going to study what's known as change of basis. So recall that we have proven that given a basis, any vector in our vector space can be written in a unique way as a linear combination of the vectors in that basis. Right? Well, those scalars form the coordinates of the vector. So what change of basis allows us to do is find a way to convert from the unique linear combination of one basis to the unique linear combination of a new basis. And this is done by finding the transition matrix of bases. Let B be an ordered basis for a vector space V, and let X be a vector in V, such that X is C1V1 plus so on and so forth, plus Cn Vn. The scalar Ci are the coordinates of X relative to the basis B. The coordinate matrix, also called the coordinate vector of X relative to B, is the column matrix in Rn, whose components are the coordinates of X. And it's represented as this, right? X, B, and it's just the column matrix of all the C's. Right now, an ordered basis is an ordered set, right? So an ordered set is a set in which the order in which you write the elements matters. So if you switch any two vectors, switch the order of any two vectors in B, you have a different ordered basis. Right, so the coordinates of a vector are just the scalar multiples needed to write it as a linear combination of your ordered basis. All right, so what we're going to do now is we're going to go ahead and find the coordinate vector of the vector 1, 2, minus 1 in R3 relative to the given basis. Right, so remember what we want to do is we want to write X as a linear combination of these vectors in B. The coordinates will be the solution. Well, recall we did that by setting up an augmented matrix and row reducing. Right, so this would be our augmented matrix, right? Remember, each column in the matrix represents a vector. And since it's ordered, now it does matter. First column will be the first vector in the basis, second column will be the second vector, so on and so forth. And it augments with the vector in which we're trying to find the coordinates of. Row reducing. Will give us this matrix. Right? And remember, we can find the coordinates of a vector in an ordered basis because the way you write a vector as a linear combination of vectors in a basis is unique. We proved that in a previous video. Well, right here, this column gives us our coordinate vector, right? So therefore our coordinate vector for X with respect to the basis B is the vector 5, minus 8, and minus 2. Right, well now we want to try and find a way in which we can transition from one basis to another. So assume that we have two ordered bases, b and b prime. If x is a vector in Rn, and we have the coordinate vector for x with respect to b, and the coordinate vector of x with respect to b prime, right? They are c1 through cn and d1 through dn respectively. Then the transition matrix from b prime to b is the matrix called P here, such that coordinate vector for x with respect to b is equal to P times the coordinate vector for x with respect to b prime. Okay. So finding this actual transition matrix, right? That's what this lemma is going to help us do. So we're given two ordered bases for a vector space V, right? If V1 is C11 U1 plus so on and so forth plus CN1 UN, and Vn is C1n U1 plus so on and so forth plus CNN UN, right? So we're writing the vectors in B as linear combinations of the vectors in B prime. Then the transition matrix from B to B prime is just the coefficient matrix of the system, right? Call it Q. So what we're going to do is we're going to say, okay, well, let V equal D1 V1 plus so on and so forth plus dn Vn be some vector in our vector space V. Then what we have is, of course, our coordinate vector for V with respect to B is, right, the vector D1 through Dn. Therefore, take Q times this coordinate vector. So there's our matrix Q multiplied by our coordinate vector. All right, doing this product, we'll get C11 D1 plus so on and so forth plus C1n dn, right? And so on and so forth, and then we'll have Cn1 d1 plus so on and so forth plus Cnn dn. On the other hand, we of course have V equal to d1 v1 plus so on and so forth dn vn, which equals d1 times C11 U1 plus so on and so forth plus C1n dn plus so on and so forth. I'm sorry, that should not be a dn there, that should be a un, so C1n un, right, plus so on and so forth plus dn times C and 1 d1, so on and so forth, C and n un. And again, I did it, that should not be a d1, that should be a u1. Grouping all of our common u terms together, we'll have d1 c11 plus so on and so forth plus dn cn1, or c1n rather, because I mixed these up, I apologize for that. That should be a cn1. This should be a c1n there. u1 plus so on and so forth plus now d1 cn1 plus so on and so forth plus dn cnn un. Right? Now, of course, this implies that the coordinate vector for v with respect to b prime is d1 c11 plus so on and so forth plus dn c1n, so on and so forth, and then d1 cn1 plus so on and so forth plus dn cnn. If we compare these two, right, so we compare this vector and this vector, we see that they are identical. Right, so we can therefore conclude that q times the coordinate vector of v with respect to b is equal to the coordinate vector of v with respect to b prime, which of course by definition means that q is the transition matrix from B to B prime. If P is the transition matrix from a basis B prime to a basis B in Rn, then P is invertible, and the transition matrix from B to B prime is P inverse. Now we're going to be using lemma 1. We let Q be the transition matrix from B to B prime. Then we have two equations. Coordinate vector of V with respect to B is P times coordinate vector of V with respect to B prime. And the coordinate vector of V with respect to B prime is Q times the coordinate vector of V with respect to B, which implies that the coordinate vector of V with respect to B is equal to P times Q times the coordinate vector of V with respect to B. And this has to be true for every vector V in Rn. Therefore, we have to have PQ is equal to the identity matrix, which of course implies that P is invertible and P inverse must be Q. Right? And obviously that is the transition matrix from B to B prime. We offer theorem 2 without proof. Right, this is going to give us a way to find the transition matrix. So we let B and B prime be two ordered bases for Rn. Then the transition matrix, P inverse, from B to B prime, can be found by using Gauss-Jordan reduction on the n by 2n matrix B prime and B, as shown below, right? So we take the matrix B prime and B together, row reduce that, and we'd be left with the identity matrix and our transition matrix. Right. So actually we're going to be doing augmented matrices, right? So let's actually do this, right? So find transition matrix from the basis B to the basis B prime given. Right? So the method is first set up B prime. We augment that now with B. And we want to row reduce this. Right? Row reducing this, we will get the identity matrix, then augmented with this matrix. Well, it is this matrix right here that forms, or that is, our transition matrix. Therefore, our transition matrix, can just call it P, is the matrix -1, 4, 2, 3, -7, -3, 1, -2, -1. Right, so this is the matrix that you would multiply a coordinate vector by to transition from B prime to B. That concludes this video on the change of basis. In the next video in the series, we're going to continue our study of vector spaces by looking at a linear transformation from one vector space to another. Right, so a linear transformation is essentially just a mapping from a vector space to a vector space that satisfies certain properties. So the next several videos will be dedicated to studying these linear mappings. As always, thank you so much for watching this video, and I will see you all in the next one.